It's about time for us to start, so let's welcome the first speaker.
Start it. Okay. Good afternoon. My name is Liang-Chieh. I'm glad to be here today to present our work exploring randomly wired neural networks for image recognition. This is a joint work with Alex, Ross, and Kaiming at Facebook AI Research. In traditional connectionist approach, how computational networks are wired is crucial for building an intelligent machine. In early days of AI, pioneers including Turing, Mingxi, and Rosenblatt all have explored randomly wired machines. There are strong biological motivations as well. Recent studies in neuroscience find that human brain networks may have a random but small world topology. Now entering the era of deep learning, we saw the success of many modern neural networks is largely attributed to how they are wired. We have witnessed the transition from chain-like wiring patterns to complex designs that have multiple wiring paths. More recently, neural architecture search, or NAS, takes it to the next level. NAS shows promising results by jointly searching 1. The wiring patterns, and 2. Which operations to perform. Here we show several neural network architectures we designed on the right. Compared to a standard ResNet architecture, our neural networks seem a bit crazy. We call our model random wire. They can achieve highly competitive results on ImageNet benchmark. So how do we design these neural network architectures? The process mainly takes 2 steps. 1. Generating a general graph. 2. Mapping it to a computable network. There are different ways to generate a general graph. Here we use 3 classic random graph models, the ER, BA, and WS model, which have very different priors and properties. This is a demonstration of the generation process of the WS model of small world graphs. We first place every node in a regular ring lattice, and then we go through each node, rewire the edge with the probability p. So when you increase the rewiring probability p from 0 to 1, you can generate graphs that are increasingly random. We can generate a very diverse set of network wiring patterns due to different behaviors of the random graph generators. Now, let me show you how we translate a graph to a computable neural network. We first start with a general graph. Then we impose an ordering to the nodes and convert it to a DAG. We then add an extra input and an extra output node to the graph. We then map our nodes to transformations, for example, a separable convolution, and we map edges to just the data flow. Finally, we'll use one graph to represent a stage in a ConfNet. Under a standard ImageNet low compute setup, without any random wiring, some deterministic generators perform poorly. Most random graph generators can work very well. However, different random graph generators can achieve different performance. We also did one experiment where we keep the wiring pattern fixed, but change the node operations. Different configurations have very high correlation, which suggests that network wiring plays a role that is orthogonal to the role of the chosen operations. When comparing with the state-of-the-art models, either hand-designed or using neural architecture search, our randomly wired models can achieve very competitive results. Finally, some takeaway messages. First, surprisingly, randomly wired networks can work very well. Second, random graphs are not prior-free. We can encode many useful inductive biases in the random process, and wiring pattern matters. Finally, we suggest a transition from designing an individual network to designing a network generator similar to the transition from designing features to designing network architectures. Thank you very much. Please come to our poster for more results and information. Thank you.
So thank the speaker, and for the second speaker, please come on the stage. Please go ahead.
Good afternoon. I'm Chen from Tongji University. Today, I'm introducing our work, Progressive Differentiable Architecture Search. This is a joint work by Dr. Liang-Chieh, Dr. Wu, and Dr. Tian. In this work, we revealed the depth gap between search and evaluation and proposed an algorithm to alleviate it so that we can boost the search speed as well as stabilize search results. Our algorithm runs very fast. As an emerging topic, neural architecture search, or NAS, aims to automatically discover network architectures that have better performance than manually designed architectures. Among all NAS algorithms, DARTS is a differentiable one which enjoys fast search speed. It puts all candidate operations into a super network and combines them with architectural parameters. After jointly optimizing network and architectural parameters, DARTS determines the final architecture by preserving the operator with the highest weights on each edge and discarding others. However, the stability of DARTS is below satisfaction. We studied this drawback from a new perspective. In DARTS, the search network contains only 8 cells, while the evaluation network consists of 20 cells. This implies that the best architecture of a shallow network is also the best of a deep one, which we believe is not true. We call it the depth gap and believe this is one of the main reasons for instability. Hence, the main contribution of this work lies in bridging the depth gap, for which we increase the search depth progressively. Our search process contains several stages. We first consider a shallow network as a warm start, and then we gradually increase search depth but reduce search space. Specifically, at the first stage, there are a small number of cells and all operations participate in the computation. After several epochs, we discard those operations with lower weights and step into the next stage, where more cells are stocked in the supernetwork, but fewer candidates operations are preserved. Later, we continue deepening the supernetwork as well as eliminating weaker operations. At the final stage, the depth of the supernetwork is very close to the depth used in evaluation, so that we maximally shrink the depth gap between search and evaluation. However, we find a severe instability issue in training a deep supernetwork, in which the skip connect operator dominates in the architecture, and thus large testing errors are reported. We explain this issue as overfitting in the search phase and use 2 regularization methods to alleviate it. First, we add a dropout after skip connect operators so that they do not gain weights very quickly in the early search epochs. Second, in determining the final architecture, we fix the number of skip connect operators. With this simple method, both network performance in terms of average accuracy and the network complexity in terms of parameters and flows are stabilized. We search architectures on CEVA 10, CEVA 100, and evaluate the discovered architecture on CEVA 10, CEVA 100, and ImageNet. The search process is split into 3 stages and with 25 epochs in each. The depths of the 3 stages are 5, 11, and 17, and the number of operators on each edge are 8, 5, and 3. The search cost is around 7 hours on a single P100. We can see that PDAR significantly outperforms previous methods on CEVA 10 in terms of both classification accuracy and search speed. On ImageNet, we have also achieved competitive classification performance under the mobile setting. Finally, we show the searched architectures and the corresponding test error on CEVA 10 for each search stage. Stage 3, with the deepest search network, achieved the lowest test error, and the discovered architecture contains deeper connections, which verifies the usefulness of bridging the depth gap. In conclusion, We propose the PDOT algorithm to bridge the depth gap between search and evaluation and stabilize the search process. Our work achieved competitive performance on both CIFAR and EpiGen with small search costs. Thank you for listening and welcome to our poster.
Thanks to the speaker and welcome the final speaker in this mini session. Please come on stage.
Hello everyone, my name is Xiawu Zheng. Today I will give the presentation of our paper, Multinomial Distribution Learning for Efficient Narrow Architecture Search. So let's start by a simple intuition. For different network architectures, in the training process, when a network structure A is better than B, then at the final convergence, structure A is better than B. In this case, we do not need to train until convergence, and directly take the results in the middle of the training process. For example, in this picture, the 4 networks order is consistent in every training epoch. And we also conduct corresponding experiments to validate the performance rank hypothesis. Similar observations are also consistent with the cell-based search space. We randomly sample six network structures in the search space and calculate the condensed tau in every training epoch. The order consistency in every training epoch is reached about 75%. And this is the search space used in our paper. A network is consisted of search cells, and each cell takes the output of 2 previous cells as input. A cell contains 7 nodes, 2 input nodes, I1, I2, and 4 intermediate nodes, B1, B2, B3, and B4. That applies sampled operations on the input nodes and the upper nodes. And an output node concatenates the four intermediate nodes. The yellow edge between 2 nodes denotes a possible operation according to a multinomial distribution in the search space. So based on the previous hypothesis, and we propose a multinomial distribution learning for efficient narrow architecture search. First, we sample an operation in the search space and according to the corresponding multinomial distribution. And at the second step, a network is trained by 1 epoch. Then we test the network on the validation set and record the corresponding information, including training epoch and accuracy. At last, we update the distribution parameter according to the proposed algorithm. The algorithm is quite intuitive. For example, in this picture, if an operation holds better accuracy with less training epoch, we thought it's a good operation and to promote the probability. For example, in the table, training epoch and accuracy of the first operation is 10 and the 0.5, which holds a less epoch and better accuracy compared with operation 2. Therefore, the probability of operation 1 is enhanced and the probability of operation 2 is depressed. We start by finding the optimal cell architecture using the proposed method. In particular, we first start with narrow architecture search on an over-parameter-sized network, and then we evaluate the best architecture with a deep network. Our model shows a notable enhancement, which indicates its superiority in both resource consumption and the test accuracy. And we also transfer our found architectures on ImageNet dataset. We follow the existing works to compare the performance on the mobile setting. The image size is 224, and the model is constrained to less than 600 million probes. The results show the best cell architecture on CIFAR 10. We can transfer to the ImageNet. And since our time is very small, and we can directly search our algorithm on ImageNet. And this table shows the results. We directly search the architectures on the ImageNet. And we reported the search cost and top one accuracy on a single V100. Thank you very much.
Now we're in the Q&A session, so please all speakers come on stage. And if you have any questions, you can go to the microphone in front of you. But before that, I already have one question from the Slido system. This question is for the exploring random wiring paper. The question is, are you just focusing on accuracy, or it might be possible that one network is better than the other due to potentially model size or other over-parameterization issues? Any comments?
Yeah, that's a good question. If you read our paper, so we control the network size and capacity to the same. But like when we change the wiring patterns, it does not change the network capacity. So everything is in a fair comparison.
I see. Any other questions? I also have a follow-up question for you. So to me, I feel like the random exploration gives you a much larger search space. Can you comment on comparing your search space to existing method? Is it how much bigger, or is that really the thing you want to emphasize?
Yeah, I think one distinct feature of our search space is like we represent one stage of the network using a graph. So we have 32 nodes like in one stage, and this defines sort of like the search space. But in existing work, they only have 5 because they are searching the cell. So this enables like bigger possibility for better search. Yeah.
All right, thank you. Oh, one question, please go ahead.
Hello. I would like to ask a question on the random search thing. You're basically mentioning flops and a random connection, but assuming the same flops, is it possible to process in an efficient way and as the normal convolution? Because I think that the computation may be different because it is not matrix multiplication anymore, right?
Yeah, thank you very much. This is also a very good question. For sure, like our currently random wired model is not friendly to the current hardware because of this multiple variant paths. But we expect like better optimized kernels in the future to bridge the gap. Thank you.
Yeah, I see. Thanks.
So we can have the last question.
Sure, thank you. So the question was also about randomly wired networks. I wondered if you had any intuition on why the random wiring shouldn't or doesn't cross between downsamples, so you only do it within layers, not between layers.
I'm sorry, can you repeat again?
So the random wiring you do,
yeah,
it's within a layer, right? It's not between like the different layers of ResNet, for example.
It's actually between different layers. So for our node is actually one layer, but although like there's kind of blurry on the definition of the layer anymore, but basically like our node is a layer. It's not within the layer.
So I mean between different resolutions, so after you downsample, you don't have random connections.
The stage you mean?
So it's okay.
Yeah, we can chat offline. Thank you.
So due to the time, let's thank all the speakers in this mini session again. And
can we also have the speakers for the next session come and take these seats up here? Except the first speaker, you can just go ahead and come on up. You can go ahead when you're ready.
Well, hello. My name is Andrew Howard from Google Research, and I'd like to talk about some of our newest mobile models, specifically how we're searching for MobileNet v3. this is a joint collaboration with many people in Google Research. All right.
I think
Okay, yeah, that's my mistake. All right, so what are the motivations for mobile vision models? So the key idea is mobile models are highly resource constrained. These need to work on, say, a mobile phone or other embedded device. So what we need to do is optimize for accuracy, but also reduce latency, power consumption, inference memory footprint, as well as the size in the APK. Basically, we want high quality models, and we want to use almost no resources for it. So competing forces. Okay, for MobileNet v3, we targeted really a small and a large workload. And so basically on the left, you can see the trade-off curve between latency and accuracy for small models. On the right, you can see the trade-off curve between latency and accuracy for large models. The intuition here is that we recognize that there are different types of use cases. So small models for either low-end phones or for possibly light workloads, and then large models for more high-end phones, as well as high workloads. So you can see in both use cases, we've kind of moved the Pareto curve. All right. So how do we search for MobileNet v3? Well, we combine two complementary search algorithms. The first on the left, that's the MNESNet algorithm, and the idea there is we have a reinforcement learning algorithm that's able to take into account both latency on actual phones as well as accuracy and search for many of the global parameters of the model in order to find a good starting model. We find that we can actually then refine the model using NetAdapt, which is also a platform-aware search, but mainly over simply the filter sizes at each layer. Okay, in terms of MobileNet v3 building blocks, we introduce a few new components, one of them being the hard swish nonlinearity. So this is building off of the swish nonlinearity, which is its x times sigmoid of x, which is a nice one. It improves accuracy at roughly the same number of flops. But in terms of implementation, sometimes it's slow in practice, depending on your setup, and sometimes it's hard to quantize. To solve that, we introduced an approximation, a piecewise one, based on ReLU 6. Same accuracy as the original swish, however, it's quantization friendly, and with a fused version, it's almost free. So you get improved accuracy at no additional latency. You can see the approximation on the right. Okay, we also introduced a new way to build features. So we call that a new classification head. What you can see is the end of a classification network on the top. This is what's used as MobileNet v2 and many other related networks derived from MobileNet v2. What we're able to do is actually shrink that down to the bottom one, the efficient last stage. And it's just a very simple idea of changing where we do our average pooling so that we're able to do feature expansion once we've already pooled. Once you do that, you can drop a couple extra layers from projection to expand and essentially get the same feature quality at 15% less latency. So we introduced a number of new pieces. This is kind of the path to MobileNet v3. We start with the MNASNet search, and by expanding squeeze and excite a little bit, we get some additional accuracy. Introducing H-swish, unoptimized, gets accuracy at a cost of latency. Once we make it optimized, we recover that latency. The next step is to apply NetAdapt, going faster latency-wise at a little cost for accuracy, and then the compact last layer is essentially free latency improvement. So this is the path for v3. We're also interested in other use cases, so segmentation models are very important to us. So if we take the MobileNet v3 and combine it with Deep Lab, we end up with MobileNet Deep Lab. So to do this, we introduced an entirely new decoder head, so the LRASPP head, pictured in this slide. And standard deep lab procedures like keeping the resolution throughout with the convolution, a true convolution. And then we also reduced some of the later layers, which was a practical way to go faster at no real cost to accuracy. All right, and thanks. See you at the poster. Happy to talk about more details.
Hello, everyone. I'm Marcus from Qualcomm AI Research. My collaborator, Mard, and me had a hot dog eating competition, and since I won, I have the honor to present our joint work on data-free quantization through weight equalization and bias correction. Most of you probably know that quantization is essential for efficient execution of deep neural networks. Many neural networks are big, and quantization can greatly reduce latency, energy consumption, and memory requirements. In this paper, we ask ourselves the question, how can we make quantization as simple as possible? Ideally, we would not use any data, backpropagation, or architecture changes such that neural networks can be quantized with a single API call. When looking at previous post-training quantization methods, we observed that 8-bit quantization works well for some networks such as ResNets. However, for efficient architectures such as mobile nets, these methods sometimes result in random performance. We started investigating why some models perform poorly. Here we show the weight ranges of each of the channels in a depth-wise separable layer in MobileNet v2. The problem is that some of the channels have extremely large weight ranges, which needs to be supported by the quantization grid. However, a big dynamic range of the quantization grid leaves no precision for channels where the weights have smaller ranges. To address this, we introduce cross-layer equalization. By exploiting the scaling equivariance of the ReLU activation function, we can move per channel scaling factors to adjacent layers. In this example, we see that channel 2 dominates the dynamic range of layer 1. Dividing it by S2 significantly reduces the quantization range of layer 1 while having minimal impact on the quantization grid of layer 2. We observed that in some cases activation ranges are always positive. And we can exploit this and absorb parts of the bias term into the next layer. This can reduce the quantization error of the activations. On the left, we see the original weight distribution from before. After applying cross-layer equalization, we see that the weight ranges are much more alike, and therefore the quantization error is significantly reduced. When applying cross-layer equalization to all layers in MobileNet v2, the quantization performance increases from random to almost 70%. Adding bias absorption increases the performance by another %. We also found that quantization error can be biased. Weight quantization can be seen as introducing additive noise. The effect of quantization noise on a layer's output distribution is a function of the expected input. If non-zero on average, the output distribution is shifted. This effect is especially prominent in depth-wise separable layer since there are a few weights connected to each output, as can be seen in this plot. We can correct for the biased error by subtracting it from each layer's output. The challenge is then to compute the expectation of X without data. We do this by exploiting the previous layer's batch norm statistics, assuming pre-activations are Gaussian and correcting for the ReLU. Using this estimate for the expected input, we can compute the correction term without any data. Applying this to MobileNet v2, we empirically verify that our analytic bias correction can remove almost all biased error. Further, we see that bias correction improves accuracy over the baseline. Combined with cross-layer equalization, we reach near floating point accuracy. And this brings us to our final full data-free quantization pipeline. We first do cross-layer equalization and bias absorption. Afterwards, we quantize the weights and correct for the bias. Finally, we use the batch norm statistics to set the activation ranges. We evaluated data-free quantization on several challenging ImageNet models and get close to floating point performance using 8-bit quantization. DFQ outperforms all other post-training quantization methods, including per-channel quantization. It also shows competitive results with more complicated training-based methods, such as relaxed quantization or stochastic rounding. In conclusion, we introduced a fully data-free quantization method which sets a new state-of-the-art for post-training quantization. In our paper, we also showed that it generalizes well to other computer vision tasks such as semantic segmentation and object detection. Please come and visit our poster at number 5.
Hello everyone, I'm Laurie Bowes presenting work on CNN inference for pixel processor arrays. PPA sensors are cameras in which every pixel element contains memory and processing. The SCAMP5 PPA used in this work features an array of 65,000 processing elements controlled by an ARM processor using a single instruction multiple data setup. Specifically, each processing element features light capture, processing, analog and digital memory registers. Each element may also transfer data with its immediate neighbors in the array. This setup allows multiple images to be stored and manipulated directly upon the sensor. Various native operations can be performed between these images, such as addition and subtraction between grayscale images, which are stored within analog registers, and then also bitwise operations between binary images, which are stored within digital registers. All this functionality allows many tasks to be performed entirely upon the PPA sensor, such as visual odometry via direct image alignment, rapid point feature extraction at over 1,000 frames per second, HDR imaging, and shape classification for tasks such as drone racing gate detection. A major benefit of performing such tasks on a PPA is that of reduced data transfer. In standard camera sensors, you must transfer entire images to be processed on external hardware, taking significant time and power. With a PPA, we can instead only transfer the data of interest, such as point features, odometry information, classifications, etc. This saves time and power and allows for more rapid visual processing. The work presented here presents an approach for CNN inference on the SCAMP5 PPA. The PPA acquires images, performs image convolutions, maps pooling, ReLU, and then finally data is transferred to an ARM controller for the final fully connected layer. All convolution calculations are performed using the digital memory registers to avoid the noise buildup that occurs with analog computation. We also use ternary weight networks whose weights naturally correspond to image addition and subtraction operations. To perform digital convolutions, we convert captured analog images into a specific digital format, dividing the processing array into 4x4 blocks. Each 4x4 pixel block then stores a 16-bit value. This schema is effectively trading resolution for bit depth. These bits are ordered in a snaking pattern such that it allows for efficient parallel bit shifting of an entire image. This fast bit shifting is then exploited by the image addition and subtraction routines of this digital format performed on the sensor. Here are some examples of adding and subtracting such images. The top row shows the raw digital representation, and the bottom row shows a visualization of the content stored within them. Digital image convolutions can then be performed using these components. This involves simply shifting a source image in a zigzag pattern such that each pixel visits every location its content would contribute to. Each shift is associated with a different ternary filter weight, dictating if the shifted source image should be added or subtracted from a results register. The results register then accumulates the final image convolution. These digital convolution results are then converted to analog and compactly stored within analog registers using a checkerboarding scheme. By doing this, it allows us to perform max pooling upon many results simultaneously in parallel. This max pooled data is then transferred to an ARM controller to perform a final fully connected layer. To train ternary weight networks, we stochastically quantize real-valued weights to ternary values during the forward and backward passes. The error produced by these quantized values is used to update the associated real-value weights. Over time, this leads the real-value weights to converge towards ternary values during the course of training. We train networks for digit classification tasks using augmented MNIST data. To evaluate on MNIST, we directly displayed the images from the testing set to the sensor and achieved around 95% accuracy from PPA inference. You can also see here some examples of hand-drawn digit classification. There's a demo of this tomorrow at booth 3 for anyone who's interested in seeing this. We also tested a simple target tracking task in which a network was trained to locate targets against a backdrop. In the case here, a toy car against a playmat with the estimated location shown in red. In summary, we present the first step in demonstrating CNN inference upon PPA sensors using compact ternary weights and digital image computation. Thank you for your time, and you can see me at poster 6.
We have all the speakers from the session please come back up? We're going to begin our second question series. Please come up to the microphones if you want to ask a question live. We also, as a reminder, have sli.do where you can ask questions remotely. All right, we're going to go ahead and get started with one question from online. So for the MobileNet v3, in general, it can be quite difficult to re-implement some of the MobileNet architectures for state-of-the-art ImageNet classification. Do you have any tricks for training these types of architectures for these large data sets?
Ooh, tricks. Well, we recently released train checkpoints, if people find that helpful. In terms of training, we tend to do this with TensorFlow and TPU. I think one of the things that would help there would be to open source that trainer, and then people can train their own and match it. Because it is often difficult to translate between two different training frameworks and kind of match. It takes a lot of time. So, yeah.
Thank you. All right, I have one question for the quantization paper. So your method focuses mostly on techniques for quantizing post hoc after you already have a trained model. But do you have any thoughts on how you might modify a training procedure to make it easier to quantify?
Yes, so there's many techniques also in literature which recently got published for doing it during training, but like using straight-through estimator or relaxed quantization, what we compared to in our last slide. But our main purpose was to make it as simple as possible, and therefore we didn't consider training-based methods.
All right, we have one question.
For the quantization paper, so one thing you mentioned is you use batch norm statistics to do stuff like bias subtraction. I was wondering how that affects doing layer fusion when you actually do deployment.
So actually we also consider layer fusion. So we just use the statistics in order to get the expectation of X with our data. So we do also layer fusion, but we can do this calculation or keep the statistics from the batch normalization in order to do both.
Thank you.
All right, if there are no further questions, let's go ahead and thank our speakers.
So the third mini session, please, speaker going in front, prepare. And we will have 3 papers related to knowledge distill. And let's welcome the first speaker on stage.
Yeah.
Good afternoon, everyone. I'm Girshick from Tian. I will talk about this paper. Below is the list of authors. In the traditional training, network is only supervised by the one-hot label. Recently, KD was proposed to use teachers' knowledge to gather students. So we need to train teacher network first. The training trajectory of teacher network may look like the red finger. So then with the help of KD, students can reach a better local minimum than before. The green line shows the trajectory of student KD. However, the gap between student and teacher is still large. How can student be closer to teacher further? We may just wondering, when does teacher perform better than students? Here we made an experiment in which we supervise students with different targets from teacher. For example, a result in the first column of the table means that supervising student with teacher's 10th epoch would result in a student with comparable performance. Since both networks are initialized from scratch, we believe that they have similar performance at the very beginning of training. What if we using the root of teacher training process to get students. Inspired by the curriculum learning, that local minimum can be promoted by the easy to hard learning process. We take a sequence of teachers' intermediate state as the curriculum to help the students, as we call the root constraint optimization, or RCO for short. The advantage of RCO is very clear. Here is a naive implementation. By randomly selecting some checkpoint from teacher's training trajectory to get students, we achieve a little improvement compared with KD, which shows the effectiveness of this idea. Then we have another question. Since teacher has numerous checkpoints, which of them are essential to construct such a learning sequence? To find the optimal learning sequence, one can search it with brute force. However, given n possible intermediate states, there are 2 to the power of n possible sequences, which is impractical to implement. A straightforward strategy is supervising the student by every state on teacher's trajectory. However, it is too time-consuming since adjacent training states are very close to each other. So we analyze the relationship with the teacher's intermediate state. Specifically, we compute the care divergence between students and different targets. Take the blue curve as an example. It is students that supervised by teachers 100 epoch. It's very close with teachers 100 epoch, but has a larger gap with the teachers later or former epochs. According to this analysis, we can propose 3 strategies for this problem. The first one is to select the anchor with straight X, which means we pick an anchor with an equal epoch interval. The second one is grid strategy, which is a bit complicated. The basic idea is to set the target according to both target's hardness and the student's abilities. The first 2 strategies boost the performance by a large margin, but with the cost of extra training time, so we propose the last one to deal with it. It's called one-stage EEI. Due to limited time for more details, please refer my paper. And here are some visualization of the proposed method. The left finger shows students' training trajectory by PCA directions, and the right finger shows RCO is more robustness when adding Gaussian noise to input space. The future work includes automatically designed curriculum for student network and generate the optimal target for teacher network. Okay, thank you.
Yeah, thanks, the speaker. And the second speaker, please come on stage.
Hi, my name is Mary Fung, and I'm going to present a joint work with Christoph Lampert at IST Austria. So in this work, we're interested in a task called anytime prediction. So recall that in the standard inference setting, the processing of any input we give to the model takes a fixed amount of time, which doesn't depend on the input. But in anytime prediction, which is the task we're interested in, we allow the model to be exogenously stopped by the user at any time, and the model has to provide a valid prediction at the time that it is stopped. So you can think of this as allowing early stopping at this time. A natural way to implement an anytime predictor is to use so-called multi-exit architectures, which are shown here on the slide. So they have so-called early exits, which are these like orange blocks, which are like classifier blocks attached to intermediate convolutional blocks. And then the architecture is simply executed from left to right, and when at test time we query a prediction, then the model simply returns the latest evaluated exit. In this work, we propose a method for training such multi-exit architectures, which has 3 components, and I will just explain them now. The first component is the classification loss. So here, we simply compare the prediction of each exit to the ground truth, and we sum up the losses from all exits. This is a very standard component, which also appears in previous work. The second component is the distillation loss. The idea here is that the late exits are presumably more accurate than the early exits because they have more computation power, And so we can use the predictions of the late exits to supervise the early exits. So it's a form of self-supervision. So in distillation speak, the late exits are the teachers and the early exits are the students. In our proposed procedure, we simply train using the sum of the classification loss and the distillation loss. However, when the teacher's predictions are very confident, then they often simply reduce to the ground truth, and then the distillation loss is not very useful, like it has no additional information. So to deal with this, we propose a scheme called adaptive temperature annealing, where we cap the teacher's confidence at a certain threshold, which helps it to put more probability into the other classes. So let me quickly talk about experiments. We have experiments on C500 and on ImageNet, as well as their subsets of different sizes. The base architecture we use is the multi-scale DenseNet, which is a state-of-the-art multi-exit architecture. And the main comparison in the experiment is between our training method, which, as I said, consists of the classification loss, the distillation loss, and the temperature annealing, versus a baseline which is training on the classification loss only, as is done in all previous work. And this is the kind of results we get. So on the y-axis, we have accuracy, so higher is better. And on the x-axis, we have inference time, like how long we let the model to compute. And the green is our method, and the blue is the baseline. And as you can see, our method outperforms the baseline. So for any fixed inference budget, we achieve a better accuracy, or conversely, for any fixed accuracy, we can achieve it using fewer exits. And the results I'm showing here are for ImageNet, subsampled to 300 images per class. But we also have experiments for different datasets or dataset sizes, which I'll show on the next slide. So here we have ImageNet and C500, and as I said, different dataset sizes. And the trend is very similar across these different settings, so where our method essentially beats the baseline, and the model seems like the method seems to be more beneficial for early exits, and especially when there's not much data. So to summarize, we propose a method for training multi-exit architectures, which is based on self-training from late exits to early exits. And we show that this improves the performance, especially of early exits. Thank you very much.
The last speaker, please come on stage.
Good afternoon, everyone. My name is Fred Tang. This is joint work with Greg Mori. We are with Simon Fraser University and Borealis AI in Canada. In the conventional training pipeline for convolutional neural networks, we have a labeled data set that we use to train the network. So the data supervision tells the network that certain images are cats, others are dogs, pianos, and so forth. In contrast to this standard pipeline, knowledge distillation provides a general technique where we can supervise the training of so-called student networks using trained teacher networks. And the idea is that the teacher provides an extra source of supervision to train the student. In general, the student observes how the teacher responds to certain inputs and tries to imitate or mimic some aspect of that response. In traditional knowledge distillation, the softened class scores are used as that response that the student tries to imitate. For example, the trained teacher might tell the student that the image on the left is 85% cat, 10% tiger, 5% other classes, and this provides a sort of richer supervision than just a one hot vector indicating the cat. And there are other possibilities we can use besides class score. Another effective strategy is to transfer the spatial attention patterns of the teacher. And the idea here is that we might want to have the student and teacher pay attention to the same parts of the image. There are many applications of knowledge distillation, and just a few are listed here. For example, in neural network compression, the teacher is a computationally expensive network that we would like to compress into a smaller student network. The teacher might be deeper, wider, be composed of more expensive operations, or its weights could be at a higher bit width than the student. Our idea is inspired by the observation that semantically similar inputs tend to elicit similar activation patterns in a trained neural network. So here, this visualization shows the channel-wise average activations sampled from the last convolutional layer of a wide resident network on the CFAR10 test images grouped by category. And what we see here is that activation patterns are largely consistent within the same class, for example, shown here in the red box, and they tend to be distinctive across different classes if we compare the red box to the purple box, for example. Instead of mimicking how the teacher responds to particular inputs, our idea here is to try to have the network learn from the pairwise similarities. In other words, we try to preserve the pairwise similarity between the inputs. If two input images produce highly similar activations in the teacher network, we would like those two inputs to also produce highly similar activations in the student. And conversely, if two inputs produce highly dissimilar activations in the teacher, we would also like them to produce highly dissimilar activations in the student. Note this idea does not require class labels, so we can apply it in transfer learning or lifelong learning scenarios in which the data originally used to train the teacher might be unavailable or might be private. This figure illustrates the overall procedure. Given an input mini-batch of B images, we derive B by B pairwise similarity matrices from the output activation maps. We then compute a distillation loss on those similarity matrices produced by the student and the teacher. And we can notice here that the student is not required to mimic the representation space of the teacher, which might be a difficult task if the capacities of the student and teacher are very different, but rather to preserve the pairwise similarities in its own representation space. We validated our approach on 3 public data sets. On CFAR10, we tested cases in which the student and the teacher have the same width but different depth, the same depth but different width, and different depth and width. And we also explored cases in which the student and teacher come from different architecture families, such as mobile nets or shuffle net students trained with wide ResNet teachers. And we found that similarity preserving distillation consistently improves training outcomes and also performs favorably with respect to the traditional knowledge distillation losses. The results shown here are a median error over 5 runs, and brackets indicate the model size and number of parameters. This slide shows the similarity preserving loss versus top 1 error for wide ResNet 16.2 students on the left and wide ResNet 42 teachers on the right, plotting all the students that we train using traditional knowledge distillation, attention transfer, and the proposed approach. And the plot verifies that similarity preserving loss and performance are indeed correlated. Our other experiments focus on the task of transfer learning and larger scale evaluation, and we also confirmed that this distillation loss is complementary to the traditional distillation losses shown earlier. For the complete results, please read our paper or come to the poster for more details. Thank you.
So let's have all 3 speakers on the stage for the Q&A. And the speaker for the next mini session, you can go ahead and go to the preparation area. So before waiting for question from the floor, we already have a popular question. It's for the early exit, multiple exit paper. The question is, do the extra exits add a lot of computational overhead? For example, is the network at the latest exit much slower than a network without any early exits?
I'm sorry, so is the comparison between like a network that has no early exits versus?
Exactly, a comparison about the computational time.
Yeah, so we find that actually most of the computation comes from the main pipeline. So the classifiers of the early exits are usually like relatively small or short, so they don't add much computation.
I see, got it. There's one question from, please go ahead.
Yeah, also to the early exits, it seems that your work works much better on the subsets of ImageNet rather than on the full one. Do you have any explanation for that?
So our hypothesis is that, so for example, if you're familiar with the previous distillation work, then distillation often acts as a regularizer. So it tends to like work better when you have less data, and essentially that's what we see here as well. So essentially if you have a lot of data, then it seems like you don't need distillation to do well. That's my best guess.
There's also one follow-up question from the early access paper. It's asking about how long the network were trained in your plots. Basically, because in your plots, you didn't show the training time, you only show the accuracy.
So the training time, so we trained the C500 network for 300 epochs, and the ImageNet network for 90 epochs. So I mean, depends on hardware, I suppose.
So maybe just comparing with training a network with early exits, comparing to non-early exits, is it training much slower than before?
I think it's not much slower now.
All right, thank you. All right, I have one question for the knowledge distilled via route constraint paper. First one. So I think, first of all, thank you for the very interesting talk. But can you clarify, is there any additional overhead in terms of using this kind of route-guided training, like additional memory, additional training time, or any overhead?
I think there is no extra burdens compared with original KD. As long as we propose the third strategies, but it's also a bit complicated. So maybe you can see me at my poster. Okay.
All right.
And I also have a question for the pairwise similarity. So
why not?
For the interclass and the inner class similarity, which one is the more important?
Well, maybe due to time, we need to stop over here, and let's give it a round of applause.
All right, can we have the first speaker of the next session come up?
Can I go? Yep. Hi everyone. I'm Georgi Stradowski. I'm a PhD student from the University of Amsterdam, and this is many-task learning with task routing. It's joint work with Nana van Noort and Marcel Waring as my supervisor. So this work is about multitask learning, and for a start, we wanted to identify 4 main issues that we wanted to address with our approach. So firstly, most multitask learning approaches have specific architecture designs for the problems that they're addressing. This limits their general usability, as switching to another problem or domain might require heavy modification to function. Secondly, in any multitask learning scenario, task connection, information about task relationships is required so that we can adjust the learning process in a way that it benefits all the tasks during training. Third, we found that there is a limited task count per multitask learning model, and after a certain threshold, models seem to saturate and training becomes less effective, so the performance would degrade. Last but not least, there is an issue with resource consumption in multitask learning models. For example, with some soft sharing approaches, we need to instantiate as many models as there are tasks, so this quickly becomes infeasible in memory. Let's build up to how we address these issues. So for start, we start with a single task learning model where we have an input layer, some hidden layers, and an output layer. A natural transition from this state to a state of multitask learning is to just add more outputs to this model and then share the units that are in between. For this, we show this in a color-coded mode where all the units that are shared have a gradient for all the colors for all the tasks. What we essentially end up with here is a hard-shared multitask learning architecture where all the units are affected by the corrective signals for all the tasks at the same time. The only way that we can control this is to somehow manipulate the loss function in such a way that we mediate the different influences for different tasks. In task routing, what we do is per task channel-wise partitioning of the model in such a way that we have units that are task-specific, that belong to only one task. We have units that are fully shared, and we have units that are partially shared between the tasks. We achieve this with our sharing ratio hyperparameter sigma, which we tune to decide how much sharing should happen in a certain layer. In this way, for every task, we create a subnet space within the same model that does that task specifically, and this does not increase the parameter count. So let's see how this approach affects the performance of our models. For this, we designed an experiment on the UCSD burst dataset, which we can see on the slide right behind us. It's a plot in accuracy versus the number of tasks that is performed by the model. Here we do at maximum 312 classification tasks. So the race has started, and in green we have the cross-stitching networks, which have crashed at 12 tasks, and the modulation for multitask learning networks, which are in close race with the red signal, and we're the red signal. So task routing efficiently performed 312 classification tasks on this chart with an 11.6% difference in accuracy. So what happened is that with the cross-stitching networks, we have 12 models in memory, and we couldn't scale up from there. So we couldn't perform more than 12 tasks. While with the modulation to multitask learning, there was saturation in training, and then after 50 tasks, we couldn't really adjust the masks anymore, so that performance started to degrade. With task routing, this just was not the case. So let's summarize and see how we avoided and overcome the 4 issues that we identified in the first slide. So we avoided the architecture-specific issue by being completely architecturally independent. We have a layer, the task routing layer, that can fit any convolutional architecture. Second, we do not need the domain expertise to forge task relationships, because we enforce a random solution and learn it all the way through. Third, we have pushed the limit a bit on the number of tasks we can do with a single model, because we can scale up to more than 300 tasks. And finally, we have a minimal multitask learning parameter overhead. Thank you so much. Come to poster 10 for more details.
Hi, I'm going to present the concept of stochastic filter groups for multitask learning. Multitask learning is successful due to its ability to learn representations that generalize well across tasks. However, this benefit is dependent on the nature of feature sharing and the network architecture. Typically, this is pre-specified, like hard parameter sharing networks to the left. One needs to determine the depth of the representation network, but also which layer one needs to branch out into task-specific networks. And this is generally based on prior assumptions about task relationships, which are not always correct. Further to this, the number of sharing patterns is combinatorial in the network depth and the number of tasks. And as a result, an exhaustive search is intractable and better approaches are necessary. And as a result, we address the issue of feature sharing in multitask learning. We propose a method that can automatically determine the degree of feature sharing or separation amongst tasks. This is achieved by automatically clustering kernels into task-specific or shared groups. And this is enabled by the concept of stochastic filter groups, which I'll explain now. So the idea behind stochastic filter groups is relatively simple. At each layer of the network, each kernel is assigned to the defined groups. For each kernel, there's an associated categorical distribution whose probabilities define the kernel grouping. It is our aim to simultaneously learn these probabilities whilst updating the filter weights. We define the task-specific groups as a set of filters which are optimized by respective task losses. And following the similar logic, the shared group is optimized by both losses. And the aim is to learn a task-specific or shared representation that improves multitask performance. And importantly, these probabilities define the kernel allocation amongst tasks. A network trained with stochastic filter groups can learn a variety of different structures. However, these structures are dependent on the tasks that need to be learned and the data at hand. And training a network with SFGs is enabled by 3 key steps. The output of the filter groups correspond to group activations which correspond to the tasks. And we wish to organize these outputs such that the gradients flow in the desired directions. In the forward pass, the shared activations are added to the task-specific groups, whilst in the backwards pass, the gradients flow in directions such as to only update group-specific weights. We minimize the following variational objective in order to simultaneously learn the grouping probabilities P
as well as the filter weight W. And importantly, we extended Bernoulli or binary dropout to work with categorical distributions such that we can sample over different grouping patterns during training. And importantly, one is to note that the likelihood terms in the loss function initially have zero gradients with respect to the grouping probabilities. And to enable the optimization process, we use a continuous relaxation using the Gumbel softmax distribution, which acts as a reparameterization of the categorical. And so we tested our model on 2 different data sets. We analyzed age regression and gender prediction from face images, but we also analyzed a real-world multitask problem, which is simultaneous organ segmentation and CT synthesis from MRI scans, which is seen in radiotherapy treatment planning. And we analyzed our method against various baselines across both data sets. We initially looked at single task networks using VGG for the age and face data set, and the ResNet style network for the medical imaging case. The first multitask baseline was a hard parameter sharing network using the single task networks. Further multitask baselines include those where the kernel allocation is not learned but set prior to training. An example would be an equal allocation of kernels across groups, which would be equivalent to grouped convolutions in a multitask setting. And importantly, you can see that stochastic filter groups which learn the structure improve over these baselines. And this exemplifies the need to learn the kernel allocation during training. And we can also visualize this kernel allocation at every layer across groups for each networks. What we can see here is that at the earlier layers, all kernels are shared. Whilst as we get deeper into the network, we see added increased task specificity in the kernel allocation. And this can actually be visually confirmed by analysis of the activations. And here we look at the activations stratified by group for high certainty kernels. And in the first layer, we can see that higher order features are learned, which would be shared across all tasks. And these would correspond to edges, for instance. But as we get deeper into the network, we learn lower order features, which correspond to salient information, which would help the tasks. So for instance, we see that in the segmentation task, we have learned segmentation-specific features, whilst for the synthesis task, we have learned features such as bone density, which will enable that process. And with that, I'd like to thank you for your attention, and I'll see you later.
We've been receiving some feedback that it might be difficult to hear, so please make sure to speak into the microphone as much as possible.
Hi, everybody. Okay, so today I want to introduce our work of transferability and hardness of supervised classification tasks. Yes, so we know that nowadays with deep learning, it is very easy to train a classifier on any task given the training data and labels, right? However, sometimes maybe instead of training a new network from scratch, it is better to look around and find whether there is some pre-trained network on a similar task. And then we can do transfer learning. Yes. So transfer learning, it means that like given the SWOG network for different tasks, so we extract the embedding from the layer before the last one, and then we train a shallow classifier on the new task from the embedding. So it requires only a little training data. So it is again. And also, this training process is very fast and efficient. So it is another gain. But the question is that like how we can predict whether the transfer learning can work, how we can get a good accuracy on the transfer network, how we can measure it is a good question. And before, people did a lot of study of how to predict the accuracy of the transfer model. For example, last year we have taxonomy, and this year we have task to vec. Yes. The problem is that like, both the methods represented tasks using the change model. So, so they are computational expensive. Here we propose a very simple approach, which uses information theory. It does not require any chain model, and it is very efficient in predicting the accuracy of the transfer model. Yes. So we assume that tasks are defined over the same domain. For example, we can have the domain of face images. Here, each image will have the identity label. And it also has the binary label for the gender. Yes. So we can train to separate network for face recognition and for gender classification. However, we know that like each person will have a unique gender, right? So and also like face recognition is well studied. We have a lot of great pre-trained network for face recognition out there. So if we would just do like transfer learning from face recognition to gender classification, is it a model will work well or even better than the dedicated training? Yes. In general, we can have the training sample X. We can label for both the SWOT Y and the target Z. We want to propose a measurement to predict the accuracy of the transfer model from Y to Z. Yes. And here we propose a very simple solution. It is conditional entropy. It has a formula like this. So P is the probability of the label in the training data. So you can see that for here the equation is very simple, and it is just computed from the statistics of the training labels, right? So it is very simple, but we prove that by analytically and empirically that it can predict well the accuracy of the transfer model. So it means that the expected accuracy of the target network will have the lower bound as the log likelihood of the SWOT subject for conditional entropy. So if the SWOT was well changed, the smaller conditional entropy lead to a better transfer model. We verified it by doing experiments on 437 tasks on different domains, for example, faces, animals, or birds. And in all the cases, we see that the error on target is highly correlated to the conditional entropy. We also get the state-of-the-art gender estimation just by doing transfer learning from the face recognition. And we can achieve it just by training a linear FEM. And finally, we propose the use of transferability as a measure of that hardness. For the detail, you can come to our poster number 12. Thank you.
We have all the speakers come up. And once again, we have microphones in every aisle if you want to ask a question. We're going to get started with a question from online for the task routing paper. So most of the tasks that you showed were quite similar. How might this method vary if you were dealing with quite distinct tasks?
That's a really good question. So for our experiments, we did an experiment on the visual decathlon challenge, which is a challenge with 10 different data sets doing completely different vision tasks, and performance seems to be all right. So we even beat some of the baselines on 7 of the 10 data sets that are in the visual decathlon data set. So we can safely estimate that there is an efficient way to use this in between many different domains.
Thank you. Okay.
Yeah, I have a question about the transferability results. It looks like a lower bound on the right, so it's not neither tight or accurate, right? Because you can get a quite trivial bound there, and really doesn't tell you much. So can you really elaborate a little bit more about how truly useful in practice, indicating that number relates to transferability?
It means that you can see our equation, right? So if the SWOT network were well trained, so that like its accuracy very high, and if we find a task which had the low conditional entropy, so our equation guarantees that the transfer model will also have high accuracy. Yes.
Oh, so you actually mean just use that to rank order all possible tasks, not actually indicating the target performance?
Yeah, it means that we can predict the performance. Yeah. It means that we can predict when the transfer model can work well. And then at that case, we should try transfer learning instead of training from scratch.
Okay, thank you.
Yes.
All right, Daniel?
I have a question for the second speaker. So what happens if your one of your tasks is sort of a regularizer for a different task? So it might be the case that performing worse at training time actually means you're performing better at test time. This is kind of the idea of regularization, not overfitting. So it could be that one of your tasks is actually really useful to learn and you should be putting more weight on like using more of the filters for that, but you could actually during your optimization be putting more weight on a different task.
Yeah, that's an interesting observation. I don't really have a full answer right now, but yeah, maybe we can talk offline. I'm not too sure how to answer this.
Okay. Thanks.
Sorry.
All right, let's thank our speakers.
And for the next mini sessions, the first speakers please come on stage. And it seems we're missing one more. Right, please go ahead and start.
Good afternoon, everyone. My name is Xin Chaopeng. I'm from Boston University. So today I'm presenting our recent research on moment matching for multi-source domain adaptation. And this paper is co-authored with Chen Bai from Horizon Robotics and Zijun Huang from Columbia University, Xia and Kisengo from Boston University, and Wang from Lecture Institute. So as we know that supervised machine learning assumes that the training data and testing data are sampled identically and independently from the same distribution. However, in the real application scenario, the training data and testing data are typically collected from related domains but under different distributions. And this is a phenomenon called the domain shift. So for example, the samples from ImageNet and the sample from the low-res video have domain shift due to the resolution. So conventional domain adaptation assumes that the source samples are collected from a single domain. But this assumption neglects the more practical scenario where the labeled images are typically collected from multiple domains. So for example, when we design an image recognition system on the images from the image search engine, the training images can typically have different modalities like the sketch image, painting image, and clip art image. So when we start to think about the multi-source domain adaptation, the largest problem we met is the domain adaptation data sets are small scale. So the most famous domain adaptation data set, Office 31, only contains about 4K images. So the scale of this data set is small compared to other tasks, such as the ImageNet for image recognition, Sports 1 million for video recognition. So we then collect by far the largest cross-domain data set called DomainNet, which contains 6 domains, 345 categories, and 0.6 million images. And the total time used to collect this data set is more than 3,000 hours. And here we show some detailed comparison of our data set to other existing domain adaptation data set. And our data set is large scale in terms of the number of images and categories and the domain numbers. So this plot shows the detailed statistics of our domain net. The colors on the above subfigures indicates the different categories, and the color on the bottom subfigures shows the subcategories ranked by the total number of instances, such as the furniture, animal, tools, and so on. So to solve the multi-source domain adaptation, we further propose a model called moment matching for multi-source domain adaptation. So our model consists of 3 components. So the first component is the feature extractor. Second is the moment matching component, and the third is classifiers. So our model takes the multi-source annotated training data as input and transfers the knowledge learned to classified unlabeled target samples. So without loss of generality, we show the OS source domain and J source domain example And the feature extractor maps the source domains and target domain into the common features. And the moment matching component, they match the i's and j's domains with the target domain as well as the matching themselves. So we perform three experiments on three data set. The first data set, digit 5, which contains 5 digit data set. The second is Office Caltech 10, which have 4 domains. And the last one is our own domain net, which has 6 domains. So on the domain digit 5 data set, our model boosts the performance from 77.7 to 87.6%, where the best baseline is 84.8. And on Office Caltech 10, our models perform the performance from 92.9 to 96.4. So on our own data set, domain net, our model can boost the performance from 13.9 to 42.6. We also compare our models to single best results and the source combined result, where the single best result pick the best result of source single to single domain adaptation. And the source combined representations represent combining the source domain from multiple domains as a single domain. And this is all my slides. If you are interested in our work, please check our poster at booth 13. We also hold a domain adaptation challenge on our data set. If you are interested in the challenge, you can also come to a task CV workshop on Saturday in the room 308. And the data set and code can be downloaded from the links. Thank you very much.
Hi, I am Safa, and I will be presenting our work with my advisor, Stefano. Annotating real data can be costly while synthetic data come with free labels, especially with the advance of the game engines and physics simulators. Unfortunately, even the best graphic engines still cannot perfectly model the real world, and this creates a domain gap in between input distributions, making it hard for a model trained on synthetic data to generalize well to real data. UDA methods aim to have small risk in the target domain by being invariant to domain variations, which are nuisances for the task. Most successful UDA methods for classification tasks use the shared feature space for both the source and the target domains. And there are many ways of adapting domains in this setting. For instance, some of the earlier works were matching the moments of the source and our target features by using maximum mean discrepancy. In this work, we will also be following the shared embedding approach. After the celebrated work of domain adversary network by Ganin, recent methods are mostly using minimax-based objectives for aligning the distributions of the domains with the help of a domain discriminator. Unfortunately, using a vanilla domain adversary alignment method may not always give desirable results, and one obvious general solution for this kind of objective is to map the cat sketches to the dog images, as illustrated here. Even though this is a well-known issue, there is no trivial solution for such a problem, as labels of the target samples are not revealed. So our hope is to jointly align the domain and label this distribution such that the cat sketches will be only aligned to the cat images. And for this, we will be relying on the pseudo labels for the target samples. So the key idea of our approach is to impose not a binary adversarial loss on the domain alignment, but a 2K way adversarial loss, as if we had 2K possible classes, where the first K are for the non-source classes and the second K are for the unknown target classes. We call the result a joint domain class predictor, or joint predictor in short, since it learns a distribution over domain and class variables. With a joint predictor alone, the probabilities assigned to the first K labels of the joint predictor are very small for the target sample, and they eventually converge to 0. Therefore, we need a separate mechanism to provide pseudo labels to the target samples to be aligned by the joint predictor. For this, we train another predictor that we call class predictor, outputting only the class labels. And the class predictor is trained on both the source data using ground truth labels and the target data using semi-supervised learning regularizers, or SSL regularizers. Then the joint predictor can be trained with the classification nodes using the ground truth labels for the source data and pseudo labels y hat, which comes from the class predictor for the target samples. On the other hand, encoder G is trained on the same nodes with the labels are swapped so that the class labels are preserved while domains are mixed. With this, domain distributions are aligned while conditioned on the labels. Given that domain shift between two distributions are removed with the alignment losses, now we can use a source-only trained model for inference. But once the domains are matched, it's also possible to further improve the generalization by leveraging the unlabeled samples. We use ideas from SSL literature for this purpose, and we particularly perform input smoothing by entropy minimization and virtual adversarial training. To demonstrate the effectiveness of the proposed approach in aligning the samples of the same class, we visualize the TSNE of the source-only baseline and the proposed approach. Samples corresponding to the same class are visualized with the same color. The symbol plus is used for the source samples, and circle is used for the target samples. And TSNE is performed on the encoder output for 1,000 randomly drawn samples from both source and the target domains. Samples of the same class are better aligned for the proposed approach compared to the source-only method. Then, assuming the target labels are revealed, we did a simple analysis of the proposed objective functions. And the main result of our analysis is that the proposed objective functions are minimized only if the encoder matches the conditional push-forward distributions, given that the joint predictor is trained to be optimal. We evaluate the proposed method on standard digit and object image classification benchmarks for UDA. CFAR to STL, STL to CFAR, and MNIST to SVHN are relatively challenging tasks where state-of-the-art accuracies are below 90%. Our method achieves state-of-the-art accuracy in all these tasks. The proposed method achieves the first or second highest score after CODA, which ensembles over multiple encoders. VADA method also uses semi-supervised learning regularizers, but our method outperforms it in all the 6 tasks. And this once again shows the effectiveness of the proposed joint alignment method. Thanks, and you can come to Foster for more details.
Hello everyone, I'm Girshick from Gianzhuang University. Here I will present our work, larger norm more transferable, an adaptive feature norm approach for unsupervised domain adaptation. This is a joint work with Guangbing Li, Jihang Yang, and Liang Ling. To begin with, we first introduce the background of domain adaptation. Domain adaptation is to transfer knowledge from a label-rich source domain to a similar but different unlabeled target domain. For example, we can train on a number of synthetic data and then deploy in real image. Next, our motivation mainly comes from a visualization map. In this example, we set the task-specific features to be two-dimensional and retrain the source-only model. As you can see, target samples are subject to collide in small norm regions, and therefore they are very vulnerable to slight shifts of decision boundaries and suffer from the erratic discrimination. However, there are 2 hypothetical interpretations. First, the domain shift might be reduced by just matching the mean feature norms of the 2 domains. Second, the domain shift problem might be mainly the result of excessively small norm target features. Rigorous alignment might be unnecessary. With this in mind, we introduce our approach. Our framework is pretty simple, along with the traditional source classification laws. We just employ our feature norm constraints upon the task-specific features to meet our goal. We have to mention that the traditional drawup is preserving the L1 norm. However, as we are exploring the adaptive L2 feature norm, we instead scale the output at the training phase by a different factor and preserve the L2 norm of the features. Next, we introduce the half adaptive feature norm. First, we define the MMFND to character the feature norm discrepancy. It is intuitive that if we restrict the mean feature norms of the 2 domains separately towards a shared value, the gap with respect to MMFND will vanish to 0, and then comes to our overall training objective. Here are some findings about HF, and while restricting the feature norm to even a fairly small value has shown effective result. However, with R gradually increases, the model is prone to achieve higher transferability, and then it is natural to explore a sufficiently large R. However, HF fails to do so as the gradients of the feature norm penalty will eventually lead to an explosion. For this reason, we introduce our stepwise adaptive feature norm approach to learn larger norm features in a progressive manner. During each iteration, SF encourage feature norm enlargement at the step size of delta R with respect to individual samples, based on their feature norms calculated by the past model parameters. Instead of assigning a hard value, SFN enables the optimization more stable and fairly easy to check off. It is worth pointing out that SFN does not rigorously breach the mean feature norm discrepancy. However, once we properly adapt the target samples towards larger norm regions, such rigorous alignment becomes unnecessary. Here are some results of our method. We work on 4 famous data sets and under both closed set and partial setting. In the closed setting, our method achieved best performance on all data sets, and especially on larger scale and extremely hard transfer tasks. And it is more lightweight. Under the partial setting, our feature norm manner does not rely on any reweighting strategy, but achieves significant improvement above the stability R. Here is the summary of our work. For more details, please go to our poster. Our poster number is 15, and I am applying for the PhD program in 2024. If you have any interest, feel free to contact with me. Thank you very much.
So let's have all 3 speakers on stage for the Q&A. And while we wait in the next mini sessions, speaker can be prepared. All right, so I have a question to the multi-source domain adaptation author. So I'm just curious about, because you created this new data set with 6 domains, have you found a case that actually not, maybe one target domain just heavily rely on one source domain and not necessarily you need multiple source domain?
So I think the motivation for composing this data set is to explore different modalities of the images. And I want to explore the modalities of the images, the effective to the neural network. So I think, so as far as we know, they are all unique. They have no overlap. So I think they are all very critical.
I see. All right, thank you. Any other questions from the audience? I can also have a question for the feature norm author. So you mentioned that the feature norm is pretty lightweight compared to other competing methods. Can you elaborate on what you mean by lightweight?
Because it's parameter free, and it doesn't need to learn a discriminator or some network, and the calculation is fast and doesn't need any parameters.
I see. And a follow-up question is, sorry, if there's no other question on the floor. And I also curious about, because it seems to me the method you propose is kind of complementary to other existing method. Have you tried to combine them and see the final result improve further?
It is a good question, but I didn't try this action, and maybe different characteristics of different methods maybe cannot directly combine, I think. Yeah.
Right, thank you. We still have time for one question. I guess if no, let's thank all the speakers again.
Hello everyone, I am Jogendra from Indian Institute of Science. I am here to present our paper UM-Adapt, Unsupervised Multitask Adaptation using Adversarial Cross-Task Distillation. Aiming towards human-level generalization, there is a need to explore adaptable representation learning methods with greater transferability. Motivated by this, we propose a unified framework to perform unsupervised domain adaptation for dense prediction tasks in a multitask setting. So here we explain the problem setting for multitask adaptation. We have access to a source domain containing images with corresponding task outputs, which is typically extracted from a synthetic graphical environment. Whereas the target domain constitutes unpaired image samples from a natural deployed environment. The objective is to improve performance in the target domain by adapting the knowledge from the source trained model. So we formalize a novel idea of leveraging cross-task coherency as an important cue to realize a unified multitask adaptation objective. We introduce task transfer network where individual networks are trained to output representation of a particular task from a combined representation of rest of the tasks as input. So as we saw, we use frozen task transfer networks as a means of balancing the performance across multiple tasks in a multitask setting. To update the base model parameter, we employ two loss terms for each task, one at the direct prediction and another at the indirect prediction. So this does not allow a single task to dominate the training process, since the least performing task will exhibit higher discrepancy and hence will be given more importance in further training iterations. So after the source domain training, following a partially shared adaptation setup, we choose to adapt a minimal set of parameters, that is Res5 block of ResNet 50 encoder, while the others are kept frozen during the entire adaptation process. So here we devise a novel direction by effectively utilizing cross-task distillation as an energy function to adversarially minimize the input domain discrepancy. So let's look at one such loss terms. So here the energy term is computed as a discrepancy between the direct prediction and the indirect prediction through the task transfer network. In an adversarial paradigm, NSEG is trained to maximize the energy for target while minimizing it for the source. And conversely, the parameters of the task-specific target encoder is updated to minimize this energy for the target samples. So besides the above solution, we recognize that spatial content inconsistency is a serious problem during unsupervised adaptation. So to address this, we leverage contour map as a common bridge between the input image and the task agnostic latent representation. We train a contour prediction net, that is C contour, and on the prior source trained model. Following this, we introduce a regularization term in the adversarial adaptation objective, denoted as LCCR. So here CCR stands for content consistency regularization. So moving into the experiments, we perform adaptation from synthetic PBRS to natural NIOD dataset. Our multitask adaptation model delivers comparable performance against the prior fully supervised single task approaches. Additionally, in a semi-supervised setting, UMAdapt clearly outperforms prior fully supervised multitask learning works consistently in all the three tasks. To demonstrate generalizability of the learned representation, we set up UMAdapt for transfer learning on ImageNet classification and Pascal VOC detection tasks. The results clearly highlight our superior transfer learning performance even with a smaller backbone net, that is ResNet 50. So here we summarize the proposed framework. First, the proposed method asks to share most weights of the network with only a few layers to be updated for adaptation. Second, two specific regularizations are proposed, that is multitask learning using cross-task distillation and contour-based content regularization. Third, analogous to the idea of energy-based CAN, the base model and the task transfer network build up an adversarial pair to improve each other for effective adaptation. So for more details and complete results, please come to our poster number 16. Thank you for your attention.
Hello everyone, I'm Dali. Today I will talk about our work episodic training for domain generalization. DG refers to problems where a model is tested on a domain that is different to those used to train it. We build upon the strong baseline AGG of aggregating all source domain data for training one model. To improve this baseline, we designed an episodic training protocol that aggregates all data while simultaneously simulating domain shift during training. If we break down the responsibilities of solving DG, it means the feature extractor should generate generalizable features to facilitate the classifier to make accurate predictions, even though the classifier has never seen that kind of data before. Or the classifier should have robust decision boundary to make accurate decisions even if it receives a bad feature from the feature extractor which has no idea about the input style. So to episodically train the AGG model, we also use domain-specific models and random classifiers to generate DG episodes. To do episodic training of AGG feature extractor, we feed the domain I data into AGG feature extractor and forward the feature into the domain J classifier. As long as this classifier makes an error, the AGG feature extractor will be penalized. It means that even though the domain J classifier has never seen the domain I data before, it can still make accurate predictions when it works with AGG feature extractor. At optimization, domain J classifier is a constant. This operation is to avoid pollution of domain I data. Similarly, we can do episodic training of AGG classifier. We feed the domain I data into domain J feature extractor and forward the feature into AGG classifier. As long as AGG classifier makes an error, it will be penalized. It means that the AGG classifier should have a robust decision boundary to make correct decisions, even though it receives a bad feature from the domain J feature extractor, which has never seen the input. And the domain J feature extractor is a constant at optimization. The used feature is important to a machine learning model. In our method, we regularize the AGG feature extractor further by a random classifier. This random classifier has no idea about any valid data. However, we hope that when it works with the AGG feature extractor, it can make accurate predictions. Whenever it makes an error, the feature extractor will be penalized. Importantly, this regularizer does not require the same label space between source domains and is suitable for the scenario with different label space. We evaluate a method on cross-dataset object recognition, VOCS, cross-style object recognition, PACS, and the cross-view action recognition on IXMath. And according to the computational cost at training, our episodic variants are efficient. The traditional DG benchmarks assume the source and target domain have the same label space. This assumption is not guaranteed in reality. If we relax this assumption, we can see that the common workflow of pre-training on ImageNet and testing on Real ID market, BERT CUB, and Action UCF is actually a DG problem. But it is one with heterogeneous label space, and where the goal is to train a more general feature extractor to be used by a downstream classifier. Therefore, we propose a novel DG setting, heterogeneous DG. In this setting, the feature extractor is trained on the source domains and used to train a classifier for the target domain task. Basically, we are using DG training to improve a general purpose feature extractor for the usage of downstream tasks. Video decathlon was initially proposed for multi-domain learning with 10 different datasets. We built on video decathlon to create a new benchmark that is the first heterogeneous domain generalization benchmark. The goal is to train on a subset of VD domains and produce a robust feature that successfully generalized to encode novel domains. We can see VDDG has twice the domains of VOCS and PACS, and is an order of magnitude larger evaluation in terms of data and task numbers. We can see the results. For more detail, please visit our poster. Thank you.
So I'm Liang-Chieh from NEC Labs. So I'm going to introduce our work on domain adaptation. Our task is cross-domain structure output prediction, such as semantic segmentation. Since collecting annotations for segmentation is quite expensive, there is a need to use synthetic data as a source domain, where the annotations are easier to collect. Then we would like to see whether the trained model can generalize well to the real-world data, which is a target domain without having annotations. Unfortunately, in practice, deep neural networks cannot generalize well. If we train a model only using the synthetic data, the results are poor compared to the model directly training on the label target. This is because the gap is usually large across domains. Through our adaptation method, we are able to generate better results. To reduce the domain gap, existing method can be mainly categorized into 3 groups: pixel level adaptation, pseudo level retraining, and output space adaptation. In this work, we focus on the 3rd group. For output space adaptation, given the source and target output, it tries to do a universal alignment between the patches. For example, patch of the sidewalk can be aligned here. However, there are also other types of patches in both domains, such as tree and car. So when aligning all the patches across domains, it cannot really differentiate these different types of the patches. Here, our goal is to align patches while learning a good embedding space that can differentiate these kinds of different patches. To achieve this goal, we first cluster patches from the source data to construct a cluster space. Second, given an output patch in the target data, we project its feature representation to the cluster space and align its feature to the source distribution. To be more specific, given the source and target segmentation outputs, we can obtain their category distributions in which previous methods aim to align such distribution. In contrast, our work first constructs the cluster space using the source annotations, which contain the patch level category information. For example, we may obtain 1 to k patch modes, and each of the modes could represent one type of the patch, such as a road or the car. Then we can project the category distribution for each patch to this cluster space through our patch module. And then we perform a universal alignment on the patch level in this cluster space. Here, we show the Disney visualization for the patch feature representations. Without our patch level alignments, features are not well aligned. In contrast, our method can produce a representation with a better discriminative and aligned features. We first show experiments adapting from the GTA 5 to the cityscapes. We present several baselines, including the model without adaptation, and with existing adaptation methods and the fusion model. When we apply our patch alignment on these baselines, we observe consistent improvement over all the models. In addition, we perform a cross-city experiment under different weather conditions, adapting from the cityscape to the observed robot car dataset, and we annotate the segmentation ground truths for evaluation. The video results show that our method can generate less noisy regions compared to a model without adaptation and the output space approach. To conclude, we present a patch level alignment method for the domain adaptation on the structural output and show our method is complementary to existing domain adaptation algorithms. If you are interested in our work, please visit our website and the poster for more details. Thank you.
Have all the speakers come back to the stage. question for the first paper, Adapt. So how does your model vary based on the sorts of tasks that you use for distillation? Do you notice that there is ever any negative transfer, or
yeah. So one of the assumptions is that the task has to be somehow related. So here, one way is like the spatially related, because all are spatial tasks. So some kind of contour, if you do, there's a contour, maximum contours will be kind of common among all the three tasks. So that is one of the things that we'll also leverage to do the adaptation process.
Okay, thank you. All right, I'll ask another question. This question is for the third paper of this session, the domain adaptation for structured output. So in your work, when you're using patches, how do you decide what size to use? And also, are there any implicit assumptions there in terms of the similarities between the source and the target domains?
Yeah, I think this is a great question. So in terms of size, because if we use too large size, it basically will be global information. So actually we pick something like 32 by 28, and then we choose roughly different size and then perform similarly. And for the assumption between the source and target domains, they contain similar patches. Actually, if there's no consistency between the source and target domain, actually we still have another loss to enforce whatever in the targets to align with the source. So our patch level alignment does not actually hurt anything about that.
Thank you. All right, I'll ask one question for the domain generalization paper. Can you elaborate a little bit about the random classifier and what you're hoping to learn through passing through that?
This random classifier is just randomly initialized, but it was not trained by any data. So it has never seen any valid data in the training. So it's like an extreme case for the domain generalization, because for domain generalization, it's like we hope the model to be robust to be to the domain shift. It can have generalizable performance on the unseen target domain. So here, this classifier is like it has no idea about any data. So I hope this feature extractor can generalize with this random classifier. So it's a strong constraint.
Thank you. Let's thank our speakers.
So now let's welcome the first speaker in the final mini session. Please go ahead.
So good afternoon. My name is Chen, and today I'm going to talk about semi-supervised learning. I'm from ETH Zurich. Semi-supervised learning aims to learn a better model by using additional unlabeled data. In a typical setup, we have a very limited amount of labeled data, but additionally, we have access to a large amount of unlabeled data. We assume that these two are drawn from the same distribution. But that sampling from the same distribution means identical empirical distribution. Let's first take a look at the 6 points. Can you guess what is the underlying distribution? Well, it's actually quite hard because there are simply too few examples. And in fact, it's a two-moon. So take a look at the two-moon again. We sampled labeled and unlabeled data from the same distribution. The large number of unlabeled data can well describe the underlying distribution. However, the limited amount of labeled data can hardly describe the two-moon. By applying kernel density estimation on x-axis, we can better see this considerable and large empirical distribution mismatch. Most current methods assume that labeled and unlabeled data are identically distributed. However, in practice, this assumption can be violated because of the empirical distribution mismatch. So let's take a look at the pseudo-label method. We learn a classifier from the 6 labeled points here, and iteratively assign pseudo-labels to the unlabeled data. However, the pseudo-label predictions here are biased. But why? This is because the model overfits to the biased empirical distribution, which leads to the biased prediction. The limited amount of label samples leads to an empirical distribution that deviates from the true underlying distribution. And as a consequence, a model trained from the label data is unlikely to generalize well on the unlabeled data. To heal the empirical distribution mismatch, we propose to use off-the-shelf alignment techniques from domain adaptation. The network contains two branches. The classification branch classifies the labeled data and calculates the classification loss. In the additional branch, we treat labeled and unlabeled data as two different domains and make use of discriminator to enforce the feature extractor to generate well-aligned features. The adversarial training is implemented by using gradient reverse layer, and the key idea is similar to again. But there's one potential issue. Too few labeled data leads to unstable optimization because we don't have enough distribution support. So how should we deal with it? One solution would be data augmentation. So in order to reinforce the alignment inspired by mix-up, we propose to use cross-set sample augmentation. We randomly sample a labeled image and an unlabeled image along with an interpolation factor between 0 and 1. We generate new training samples by interpolating between them. And in addition, we make use of the pseudo-label for the label interpolation. The benefits of the proposed augmentation are twofold. First of all, by interpolation, we can generate as many pseudo-samples as we want, and this makes the training data set a lot larger, thus leads to more stable training. And secondly, the Euclidean generalized energy distance between the empirical distribution of the pseudo and unlabeled samples is smaller than or equal to that of labeled and unlabeled samples. We actually have a proof. Please refer to the proposition 2 in the paper. Let's take a look at the final proposed model. On the right side, in addition to the classification branch, we have a discriminator to distinguish labeled and unlabeled samples. Then, for each mini batch, we use a cross-set sample augmentation strategy to generate and interpolate samples and labels, and use them as training data to train our AdaNet. We perform ablation study on CIFAR-10, and we include a baseline which is trained only with label data. We observe that both the distribution alignment and cross-set sample augmentation are important for improving performance. We further compare our AdaNet with recently proposed methods on several benchmark datasets, and AdaNet achieves state-of-the-art results on CIFAR-10 and SVHN using the conv-large backbone, and also on the large-scale ImageNet dataset using ResNet 18. So to sum up, empirical distribution mismatch is an important but often overlooked problem in semi-supervised learning. Our code is available online, and thank you for your attention.
Yeah, you can start the video. Yes, thanks. Hello, everybody. I'm Luca from Google Brain in Zurich, and the work I did here was together with my colleagues Xiawu and Alex, also from Zurich, and Avital from Amsterdam. All of us contributed equally. So we all know that nowadays in computer vision, if we have some task that we want to solve, we collect a large data set, label all of it, and then we can get pretty good, satisfying performance. But we also have a long tail of tasks which we would like to solve, but for which collecting labels for all of them is super expensive. And this is where semi-supervised learning comes in, with the promise of achieving similar results, but with order of magnitude less labels. At the same time, there's the field of self-supervised learning, which has recently made large advances. And there the idea is to learn useful representation from completely unlabeled images. The question we asked ourselves, and that we're going to answer here, is what if we leverage advances in self-supervised learning to improve semi-supervised learning? So in this, the remaining of this talk and our paper, we use mostly two self-supervision techniques which exist already, but this applies to more. So the first is exemplar, where we cut patches out of an image, heavily augment them, and then ask the network to learn a representation that is more similar for patches from the same image than from patches from another image. For example, you can do this with a triplet loss. The second self-supervision technique is rotation, where you apply a rotation, a multiple of 90 degrees to the image, and then ask a network to recover which rotation was applied as a four-way classification. Both of these have been shown recently to learn pretty good features. So what we propose is to take a different look at semi-supervised learning and basically look at it through the lens of self-supervised learning. So imagine you have a large data set of images and few of them are labeled. Then what we suggest is to apply your favorite self-supervision technique on all of the images, and for those images where you do have a label, also do simply supervised training, and then combine these losses. This is what we call the self-supervised semi-supervised learning, or for short S4L. It's a conceptually very simple method, and surprisingly, it achieves performance that is on par with existing semi-supervised methods. This way you can turn any self-supervision method that you want into a semi-supervised method, and our hope is, with this presentation, to bring both of these fields closer together such that they can actually profit from each other. So looking at our results, there are a lot of them. I'm going to go through them quickly, but come to our poster for more. The first contribution we have is that we actually present a much stronger supervised baseline on a subset of ImageNet than was previously reported in other papers. Then another contribution is that we have existing semi-supervised techniques that you have heard of before, like pseudo-labels, VAT, and entropy minimization. And we show that they actually do scale up to real-world data sets like ImageNet with fewer labels. Then we try out the common or naive way of doing self-supervision, which is first training self-supervision only as a pre-training step, and then either learning a linear classifier on top with the few labels or fine-tuning the network. Both of these do not give good performance. But then finally we showed that our joint learning framework S4L with either of the self-supervision techniques actually gets good performance that is on par with that of the existing semi-supervision techniques. Finally, we want to show that it's not a competition between those fields, but actually they can profit from each other. So we do this by proposing what we call MOAM, the mix of all models. This is a three-step model that we're going through. You see the steps on the right. In the first step, we take any S4L model that we want, for example, S4L rotation that we just presented previously, and add the classic semi-supervision losses like VAT and entropy minimization. Now that we have this model, we can do a round of pseudo-labeling, which is also known semi-supervision technique, and learn a model on the pseudo-labels. Finally, as a first step, now we take this pseudo-label learned model and fine-tune it on only the few labeled clean labels that are available. And as we showed, this full MOAM model with the three steps actually achieves state-of-the-art on 10% labeled ImageNet, but even just the first step gets good performance. And also it works pretty well on the full data set if we have all labels available, so it doesn't deteriorate things. We provide code, and we are happy to see you at our poster. Thank you.
Let's have all the speakers for the Q&A question. Do we have any question from the audience? So for the first paper, I want to ask the question about the data augmentation. So
yes.
Do you just randomly try different lambda, or there are certain procedure you do when augmenting new examples?
We randomly sample one from the labeled data and randomly sample one from unlabeled data. And then we sample an interpolation factor from a beta distribution, which leads to a factor between 0 and 1. Then we interpolate between them. So it's completely random in these two data sets.
Mm-hmm. And can you clarify for the new augment data, how are you going to use it for the adversarial loss for the new sample data?
So the adversarial loss before was 0 and 1 when you compute, but right now then we have this interpolation factor, so we just use that, and we use a discriminator to predict that factor.
So instead of predicting 0 or 1, you predict
a
regressive
between
value.
0 and 1.
Okay, got it. Thank you very much.
Thank you.
Professor Loja, please go ahead.
I have a question, I guess, for both maybe papers about semi-supervised learning, which I think is a great direction, but I'm a little bit worried about the typical evaluation. You subsample your ImageNet and then you show something. Shouldn't the right evaluation be that you take ImageNet and then, you know, 100 million other images and then you do better than just using ImageNet? Why aren't we looking at that?
Yes, I agree. This would be, I think this is a really cool direction to go and to try out. I think so far we take the subsampling ImageNet kind of as a proxy, and this is already like much larger amount of unlabeled images than like the simpler benchmarks that have been used before, like CFAR and SVHN, right? But yeah, this, I fully agree, but it is like, it takes even more time to do it because it's even larger, but it's definitely where we should go. And one thing though is that it then also introduces the, how's it called, domain adaptation basically into the fold, right? Because you're gonna get the additional image that we get out of somewhere, like the internet, for example, they will look differently than the ImageNet images. There was this paper before, I think, that resampled and followed this procedure on CFAR and also saw discrepancy. So it would also mix two things together, and we basically need to do both of the things right, I think, to get benefit.
I also do believe that this is a great direction. Like we have some other data set other from an ImageNet, and we try to improve the classification result on ImageNet. And as Andy mentioned before, that might be there is a domain gap, but our method already had this domain adaptation and alignment mechanism inside, so we would assume that this will also work well on that kind of task. Thank you.
All right. Due to time, let's conclude this final session, and let's thank the speaker again. Thank you very much for attending this oral session. Thank you.